Recall that vector spaces are sets of vectors of all the same size, where if we were to take any two vectors from the vector space and add them together, we get that vector back in the vector space. And more generally, if we took any linear combination of vectors in the vector space, by definition, we should get back a vector that's also in that vector space. There are two special types of vector spaces which we can define, which actually depend on the matrix itself. So if we're given any matrix, let's just say we're given the matrix, checking my notes here. Okay. Let's suppose we were given the matrix. It's my whiteboard here. 3, 5, 8, 4, 2, 0, 6, 3, 4. As it turns out, we have two special spaces that arise as a result of the matrix. We have what's called the row space, and we have what's called the column space. The row space of a matrix is the collection I guess I should be careful. I'm using 1 to substitute that these are all 1. Okay, these are not the same numbers. It's kind of a sloppy notation, but is what it is. If I have an m by n matrix, okay, the row space is the space that is spanned by the row vectors. That is, I take the row vectors and I generate linear combinations of them. The column space of A is the same thing, except it's the span of the column vectors. For example, we have the following rows: 3, 4, and 6, 5, 2, and 3, 8, 0, and 4. If we take the transpose of these, we get vectors, okay? And what I can do is span a space. I can span a space by using these specific vectors. That is, I can use, as we've illustrated before, I can define a set of vectors, y1, y2, y3, such that y1, y2, y3 is equal to any real number times the first vector plus any real number times the second vector plus any real number times the last vector. Okay? In other words, I can take the row vectors and span out a new space. Likewise, I can do this for the columns. Okay, so for the columns, we had the vectors 3, 5, and 8, 4, 2, and 0, and 6, 3, and 4. And we get, when we take the span of that space, right, that's just the set of all vectors, y1, y2, y3, such that that vector can be written as a linear combination. I'll use beta just to emphasize the differences between the last one. 4, 2, 0, 6, 3, and 4. Oh, I'm sorry, plus beta 2, plus beta 3. Get rid of those. In other words, you give me any 3 numbers in the real number line. When I multiply them by these vectors, I get a new vector. And that vector is in the span of those other vectors by definition. So there's 2 types of vector spaces. As it turns out, the dimension of the row space of a vector is actually equal to the dimension of the column space of a vector of a of a matrix. Sorry, just double checking. So as it turns out, the dimension of the row space of the matrix and the dimension of the column space of the matrix is what's referred to as the rank of the matrix. Okay, so those are just some of the fundamentals. Now, what I haven't done, I notice I just said the span of the vectors. I didn't ask whether or not those vectors are linearly independent or dependent. So does this mean that because I have a 3 by 3 matrix that I therefore must have the dimension of the row space equal to 3? The answer is no. All right. The reason is very simple. Because some of these vectors may be linearly dependent. Now, for this example, I don't know if it's linearly independent or dependent. We're going to, in the following videos, develop a test or a procedure to be able to actually determine whether or not they're dependent or independent. But this shouldn't be terribly too hard to see. I mean, suppose that we could write them as linear combinations. Then we have 4 alpha 1 plus 6 alpha 2. 5 would be equal to 2 alpha 1 plus 3 alpha 2. And then 8 would equal nothing alpha 1 and 4 times alpha 2. So here you can very clearly see that alpha 2 would just equal 2. Divide both sides by 4 here. So we know that for whatever alpha 1 there is, alpha, if I can write these vectors in terms of the other 2 vectors, I need to have alpha 2 set equal to 2. That's the only way that bottom equation holds true. Which means then that this next equation would be 3 times 2 is 6. So then I would have 5 equals 2 alpha 1 plus 6, which that's the same thing as minus 1 alpha 1, which that's the same thing as minus 1/2. But if these were dependent, then I should be able to plug this in here and this in here, and I should be able to get the right results. So what do I get here? I get minus 1/2. 1/2 of 4 is 2, so I get minus 2 here. And then plugging 2 in here, I get 12, which gives me 10, which obviously is not equal to 3. And so I can see then that there's no combination of alpha 2 and alpha 1 that will work here. First of all, alpha 2, as we've demonstrated about a minute ago, needs to equal 2. There's no other quantity for alpha 2 that we can plug in here that will make this true. So that needs to hold true. So we are, by the logical deduction we just took, we showed that if alpha 2 is equal to 2, then alpha 1 needs to be equal to 1/2. And then we plugged both of those in the first equation and showed that it's not equal to 3. So it's impossible. We can't find an alpha 1, alpha 2 to represent this vector in terms of a linear combination of these, and therefore they're independent because I can't write them that way. Because they're independent, that means in this example, the dimension is 3 of the column space, which means since we know this is true, the dimension of the row space must also